Hello all, I'm Gianni Corsetti. Today I will present you our latest CVPR paper, which is titled Functionality Understanding and Segmentation in 3D Scene, and it also got a Poster Highlight award. So this work tackles the functionality understanding task that was recently introduced by the Fun3DU paper. In this task, we assume to have in input a high-resolution point cloud of an indoor scene, along with a sequence of RGBD post-frame that depict views from inside the scene. Additionally, we have a natural language description of a task. The objective is to find the 3D mask of the object that can be used to carry out the action described in the task description. So in this case, we have to segment the handle of the bottom door of the oven. This task is challenging as the reasoning must be used to take into account, for example, the spatial relationships within the object in the scene, and moreover, the resolution of the point cloud makes the cost of processing it quite high. It can be applied, for example, to tasks in which we have a robotic assistant that is exploring an indoor environment. To tackle this task, we design our method, Fun3DU, and Fun3DU is based mostly on visual language models and LLMs that are used to process the sequences along with the point cloud. This makes our method completely training-free in the sense that we do not need any task-specific annotation for functionality understanding. We start with the task description understanding. So given the task description, we wish to find two particular objects, the contextual and the functional object. The functional object is the name of the actual object we want to segment. So in this case, we have, for example, the drawer handle. While the contextual object is the object that physically contains the functional object or that is spatially related to it. So in this case, we are interested in the cabinet. In order to extract these two objects from the prompt, we use a LLM empowered with chain of thought reasoning. So in this case, the output would be drawer handle for the functional object and cabinet for the contextual object. Subsequently, we look at the RGB views of the scene in order to find the contextual object. And we do so with an open vocabulary segmentation method, specifically with grounding Dino plus Sam, and this gives us the set of masks of the cabinet within the scene. Now, a problem is that this set of masks can be very large, even 1 or 2,000 views for each scene. So we want only to segment the best. We only want to segment and retain the best views for our task. So we adopt this. We design this score-based view selection mechanism in which we consider the distribution of the pixel of the mask relative to the image center, and in particular we consider the distribution of the distance relative to the center and the angle relative to the center. So this gives us two scores, which are higher when this distribution are more similar to the uniform distribution. This is because a uniform distribution means that the object is well centered and well visible in the image center. Additionally, we consider the semantic confidence score obtained from the segmenter, and at the end average all of them with the specific hyperparameters to obtain a single score. So we use this score to segment only the top K views according to it, in order to proceed with the next step. Now the next step is segmenting the actual functional object, and we do so with a particular visual language model, which is Molmo, and Molmo is capable of pointing to a specific object in the views. So we provide them with this prompt, which says point to all the functional object name in order to task description, and in this case we have point to all the drawer handle in order to open the bottom drawer of the cabinet with the TV on top, along with all the images in which the contextual object has been detected. And this gives us the points in each view, and then we prompt the point to SAM, which is a promptable segmenter, to obtain the final masks of the functional object within each view. Now, these masks are a bit noisy, so in order to regularize them and obtain the final 3D mask, we unproject them and sum them on the 3D point cloud to obtain an heat map. We finally binarize the heat map with a specific threshold to get the final mask. Here we have the quantitative results of Fun3DU. So we compare with state-of-the-art methods for open vocabulary segmentation. We can observe that these methods are similar to Fun3DU for the recall at least, and actually some of them have a higher recall, but on the other hand, the precision is extremely low, and in most cases in 0. And we observed that other methods tend to segment the whole contextual object instead of just a functional object. So we can observe just an example of this in the qualitative results. In particular, if you look at the second column from the left, you can observe that OpenInst3D segments the whole nightstand, while Fun3DU is capable of accurately segment the exact knob required, so the one on the bottom drawer of the nightstand. So in conclusion, we provide the first method to functionality understanding in 3D scene, which is also a training-free approach that does not require task-specific annotations. And additionally, the architecture of Fun3DU is very modular, and this allows it to be easily upgradable with new state-of-the-art LLMs and VLMs as soon as they come out. There are some limitations to our method. The first is that its performance is worse in case of ambiguities in the contextual object. So for example, if I'm looking to open a specific drawer on a cabinet and there are multiple cabinets. And second, since we use many LLMs and VLMs, the memory cost is quite high and the speed is a bit low. Nonetheless, compared to the baselines, the time and memory costs are similar. End of the presentation. Thank you all for your attention.